Greetings and welcome back. Today we'll be looking at kinetics and thermodynamics. This is essentially what you covered in all of General Chemistry 2. We'll be doing it in one video, how about that? But this should be a review. That being said, if you have any questions or there's anything that you're completely missing, we are going to go fast, so bring any questions you have to class. So first off, let's define what those things mean. Thermodynamics, thermo meaning temperature or really energy, and dynamics meaning change, is all about how much energy is given off or consumed over the course of a reaction. So does the reaction go down in energy? Does the reaction go up in energy? Or does the reaction stay the same in terms of energy? And so that's all we're looking at in here is a change in energy, which usually we use Gibbs free energy. So think about this in terms of delta G, or change in Gibbs free energy. Kinetics is about how fast something happens. And so think about this as basically the speed of the reaction. How fast is it going to go? And this is based on a number of different factors, but if we have a reaction that goes down in energy, sometimes the reaction energy diagram looks like that, and sometimes it looks like that. And really, it's about how hard is it to kind of climb this little hill in order to get to your products. So, kinetics is all about how fast a reaction happens. Thermodynamics is really going to tell us whether a reaction happens and if it likes to go forward or in reverse. That is all you need to know, maybe, but let's get into a lot more specifics. We're going to start off by examining more details of thermodynamics, or the change in energy over the course of a reaction. So let's look at one specific reaction, or I guess one general reaction, in which the reactants, A plus B, can turn into C plus D. And so what we're really considering is the stability of the starting materials versus the products. If the starting materials are less stable, then in general what we will find is that they are going to want to move towards a condition that is more stable. And what we would see in this case is that comparing energy over the course of the reaction, we would go from a less stable situation, which is higher energy, to a more stable condition, which is lower energy. So I'll put my A and B up here, and my C and D down there. And so over the course of this reaction, you would go down in energy. We would say that we have a negative delta G, because the change in Gibbs free energy is negative. We've gone down, right? We've gone down here. And therefore, this type of reaction would tend to be favorable, because you're going from a less stable condition to a more stable condition. It's like if you hold a book up above your head and then you let go, it's going to move on its own to a more stable condition, which will be hopefully not landing on your head, but eventually landing on the floor. All right, so another thing that we can consider with this is that reactions don't just go in one direction. They usually go in both directions at the same time. And so where we'll end up with more things is the more stable condition, but we'll always still end up with some of the less stable. And the way that we quantify this is based on the equilibrium constant, or the KEQ. So the equilibrium constant we define as the concentrations of starting material and product at equilibrium. And we do this by saying it's the concentration of, in this case, C at equilibrium, times the concentration of D at equilibrium, divided by concentration of A at equilibrium, times the concentration of B at equilibrium. So what this is saying, in broad strokes, is that it's the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. So hopefully most of this rings a bell. But what this is telling us is that we have a mathematical number that we will get for every reaction. In the course of this reaction, the one that I have modeled right here, C and D, which are the products, are more stable at equilibrium than A plus B. Well, they're more stable overall, but at equilibrium, or when we let this reaction go for a while, you'll find that you'll have a lot more C plus D because it's more stable, and a lot less A plus B. So when we're comparing this ratio, we should have a lot more products than reactants. And therefore, if this number on top, the numerator, is higher than the number on bottom, which is the denominator, we would have, again, and just in this case, the KEQ would be greater than 1. We don't know how much, but considering this case right here, we would have a KEQ greater than 1. So let's consider the other circumstance, where we have an A plus B going to a C plus D. Well, what happens if your starting materials are more stable and the products are less stable? Well, in this case, what we would see is in our reaction energy diagram that we would go from a state that was lower energy or more stable to a state that is higher energy or less stable. And if our A plus B is down here and our C plus D is up there, well, the change in energy is going to be positive. And by positive, we mean it's going up in energy. So we've got a delta G that is positive. That type of reaction can proceed, but doesn't really like to, because you're going from a more stable state down here to a less stable state up there. However, what we see is that in case of reactions like this, they will go forward, but just a little tiny bit. And we can plot out once again our KEQ. Since our KEQ is still going to be the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. Hopefully you see that in this case, when our delta G is positive, we're going to a less stable state, that at equilibrium, so eventually, we'll end up still with a lot more A plus B than C plus D. So we would have a lot more reactants than we would products, and therefore our K, or equilibrium constant for this reaction, would be much less than 1, because you would have a very big number down here, because you'd have a lot of reactants, and you'd have a relatively small number on top. So consider this to be something like 1 divided by 4. You're going to get a fraction that's going to be less than 1, and therefore your equilibrium constant is less than 1. In the weird case that A plus B and C plus D are exactly the same energy, then your KEQ would be equal to 1, because that reaction would just give you kind of equal amounts of starting material and products. So these are the general two states that we see. Either you're going to a more stable state, which we did up here, in which case your K is greater than 1. You're going down in energy. So sometimes we refer to this kind of reaction as exothermic. It's giving off heat. And this kind of reaction as endothermic. All right. These terms technically mean a change in heat. So sometimes you'll also see the more correct terms, which are about a change in energy. The change in energy, the term really is exergonic and endergonic. Those terms are usually used interchangeably, but technically exothermic means it's giving off heat. Exergonic means it's giving off energy. Endothermic means it's absorbing heat. Endergonic means it's absorbing energy. So if you ever see those terms, just think of them interchangeably pretty much. If you take physical chemistry, you will very much get to know the exact differences, but for our case, it's totally fine. So I'm going to use one quick example, which is that glucose, or C6H12O6, plus oxygen can undergo a combustion reaction. And combustion reactions end up giving us water and carbon dioxide. So this would be 6CO2 plus 6H2O. And this would, of course, go down in energy. We know that because if you start a fire after you put in a little tiny bit of energy, it gives off a whole lot of heat. It gives off a whole lot of energy. And so this type of reaction would go down in energy for sure. And we would say that this is an exothermic reaction. All right, but sugar can sit there on the table with oxygen around, and it doesn't just immediately turn into carbon dioxide and water. It doesn't light on fire by itself. And that's because of kinetics. So let's look at what kinetics means. Kinetics is the speed of a reaction. And the speed of reaction is determined by the fact that we have a little barrier to overcome in order to get to product, which kind of looks like this. And so there is a specific amount of energy that has to be input in order for a reaction to go forward. And we call this the activation energy, or E sub A. So if you started a fire before, you know that essentially wood is just a bunch of sugars attached to each other. And that it's got oxygen around it, but wood doesn't spontaneously combust unless there's an input of energy to get it to essentially this little top of a hill up here. So that's why we have to light a match. We have to put a little bit of heat in to get it up here in order to overcome that activation energy. And then it will go downhill and give off a lot of energy. So the first little bit of wood, you have to put a little bit of energy in to get it started, and then when it goes down in energy, that first little bit of wood gives off a lot of energy, and that's enough to overcome the activation energy of the next little bits of wood and little bits of wood. So once you get a fire started, it can just keep burning and burning because the energy given off by the overall reaction in terms of our thermodynamics will be enough for the next little bit to overcome its activation energy. So kinetics really has a lot to do with that activation energy. So we say that in kinetics, the rate of a reaction is equal to a little k times the concentration of the reactants. So going back to our general condition, if we have A plus B going to C plus D, then the rate of that forward reaction would be equal to a little k, which is your rate constant, times, in this case, A times B. There are sometimes exponents involved. We won't see them very often in organic chemistry, but it's possible that you could have stoichiometry to deal with. Cross that out, do a little d times d. And those end up as exponents up here. Usually, though, what we see is that those little exponents are just 1, because 1a and 1b get together, and if that's the case, then those exponents would be 1, and therefore we would be able to just completely ignore them. All right, so, oops, I missed my stoichiometry up here. Sorry, there's 6 oxygens to burn 1 sugar. So this little k involves activation energy, and I'm not going to really worry about why. It also involves temperature. It involves collision, basically your chances of things bumping into each other. So you know that if you chop wood into sawdust, it'll burn a lot faster because there's more interactions with the oxygen. So there's more stuff going on in there, but in general, consider that the rate is throttled by that activation energy. So in this case, this imaginary problem that I drew up here, I just said that this is our activation energy. But if you have a very high activation energy, even if your thermodynamics are the same, if you had a really big hump to climb over, it would be much harder, and therefore the reaction would go much more slowly. All right, that energy at that very top of that hump, we sometimes call the transition state, and write it like that. This is whatever you have to go through, transition state, in order to get from your starting material to the product. So let's consider this in terms of acid-base. So let's say we have our OH minus, and I'm going to react that with a little bit of, I don't know, we'll use HF again. So in the course of this reaction, your O minus shares electrons with that hydrogen, and the fluorine unshares electrons. and therefore the product that you would get would be water less F minus. Acid-base reactions have very small transition states and therefore are low energy transition states, and therefore they have very small amounts of activation energy to overcome. That transition state is essentially that halfway point between these reactions. So the transition state in this case would look kind of like this. You would have an OH, which is taking the hydrogen away, and that hydrogen is in the process of leaving that fluorine. So this isn't really a thing that exists, but imagine that being kind of what has to happen halfway in between, or roughly halfway in between, this starting material and this product. So there would be, this is basically what we're thinking about in terms of a transition state. It's somewhere in between. So essentially this guy's passing its hydrogen over to the hydroxide, and halfway in between you have that state where that hydrogen is kind of halfway attached to fluorine still and halfway attached to oxygen. And depending how unstable that is, our transition state or our activation energy may be high and it may be low. If it's high, the reaction is slow. If it's low, the reaction is relatively simple. A lot of reactions that we will look at in this class have a very high transition state, therefore a very big activation energy. Acid-base does not. In general, acid-base goes forward very easily. In the case of this reaction that I've drawn out here, this acid-base reaction, it is a favorable reaction because F minus is more stable than OH minus. We'll talk more about that in the next video. But regardless of the fact that this goes forward in energy, you have a very low energy transition state, and therefore your activation energy right here is pretty small. All right, so that's kinetics and thermodynamics in a nutshell. Let's look at what happens when we have multiple steps for kinetics and thermodynamics. So let's say that we have a reaction where the first step is that A goes to B, and the second step is that B goes to C. So this is a two-step reaction, and often what we see when we do reactions like this is that they'll start somewhere and they'll go up in energy, and then oftentimes they'll go back down in energy. And so this reaction would be overall a forward reaction because the starting material compared to the final product is more stable. But you have to go through B to get there. So the initial starting material is A, and the final product is C. We would call B, which I've written up here twice, the reaction intermediate. You might also notice that you have two different transition states here, 1 and 2. All right, in this case, in step 1, which is A to B, we would say that our delta G is going to be positive because that first step goes up in energy. From B to C, you're definitely going down in energy. So we can consider that by drawing these out kind of right here. So this is step 1. You're going up in energy, so the delta G is positive. And in step 2, which is going from B to C, you're definitely going down in energy, so the delta G is negative. Hopefully you can see that. That's going down. All right, but overall, that delta G from A to C is going down. So if we imagine where we started and where we ended, the delta G overall is negative. All right, so this would be a multi-step reaction. A goes to B, and then B goes to C. Overall, it's still A goes to C. However, we have to go through an intermediate. We also have multiple steps. The rate-limiting step, which you probably recall talking about in general chemistry, means that is the slowest step overall. Slowest and fastest is determined by kinetics, and kinetics has to do with the hump that you have to climb. So notice that the hump that you have to climb that is the tallest is this one right here. So this is the highest energy transition state. transition state is that guy. It's like a kind of a double cross. So the highest energy transition state determines what our rate limiting step is. So this first step would be the rate limiting step. If we're trying to put this information in terms of those two buckets of kinetics and thermodynamics, the kinetics are determined by these humps, and the thermodynamics are just determined by the difference between the energy of the starting material and the product. And that is it. So, as a really quick recap of these two different things, we are always going to go from somewhere to somewhere else in terms of energy. The difference in energy between the starting material and the transition state right here, this is going to determine your kinetics, or how fast the reaction occurs. And the change in energy from starting material to product, which is right here, this is going to determine your thermodynamics, which is a long word. And the thermodynamics is the overall change in energy, which determines whether the reaction wants to go forward or backwards, and by how much. All right, please practice this, think about it, bring any questions that you have from general chemistry or from this video, and I will answer them the best I can. Thank you very much.